Hello, everyone. Thank you so much for joining us this afternoon for our Spring into STEM lectures. This is the second lecture that Medical Physics and Biomedical Engineering will be providing. And it's hosted by Carlos and Oriol, who will be talking to us about next generation X-ray vision. So without further ado, I'm going to hand over to Carlos and Oriol. And just quickly, please do put your questions in the chat or the Q&A. And then at the end of the lecture, Carlos and Oriol will answer all of your questions. If you wanted to unmute yourself as well, you can just raise your hand and I'll unmute you in the participants box. So thank you very much, and over to you guys.
Thank you very much. All right. Hello, everyone. My name is Oriol, and with my colleague Carlos here, we are two PhD students with the Advanced X-ray Imaging Group at UCL, and we'll be talking to you about next generation X-ray vision and multi-contrast X-ray imaging techniques. Now, there will be two parts to the presentation. I'll be starting to speak about X-rays and why they're important and why what we're doing is important. And then Carlos will go a bit more technical, a bit more scientific. So we hope you enjoy it, and we'll answer any questions that you have at the end. Now, when I say X-rays, I think probably what comes to mind is either going to the dentist. This is in fact an image of my mouth, of my teeth and my implant. Or maybe having a CT scan, which is this big machine where you have the X-rays whirring around you, and then you get these nice images of your brain, your lungs, or whatever you need to image. So these are probably the things that come to mind. And I'd like to talk to you a little bit about how these things actually work. What's the physics behind them? So usually X-rays work in the following way. You have an object, which could be my teeth, could be your lungs, could be anything. You have the X-rays coming in, and then they come out. But after going through the object, they've interacted with the object in interesting ways. They are attenuated. What that means is that the intensity of the X-rays coming in is higher than the intensity of the X-rays going out. And you can see that if the X-rays don't go through the object, they have the same intensity. But if they go through the object, they have lower intensity. And using this, we can have a nice image that tells apart, let's say, teeth, for example, from gums. This is one of the basic things that happen when X-rays interact with matter, and it's called attenuation contrast when we're talking about imaging. And this works fairly well. However, there are some cases where this doesn't work so well. For example, with soft tissue, with biological tissue, like let's say breast tissue and cancer, and let's say breast tumors in healthy tissue. It's sometimes hard with attenuation to tell the difference between a tumor, for example, and healthy tissue. So we can start looking into other things that happen when X-rays go through matter in order to get better images of things like soft tissue. Now, one of the things that happens when X-rays go through matter is related to phase. If you think of X-rays as this blue wave, this blue line that goes like this and has some peaks and has some valleys, has some peaks and has some valleys, the phase is essentially related to the point in the wave that we are. Are we in the peak? Are we in the peak? Are we in the valley? Where are we? Well, you can see that when the X-ray goes through matter, oh, I just disappeared from the, okay. When the X-rays go through matter, goes through an object, you can see that yes, it is attenuated. The intensity of the X-rays here in green is reduced when it goes through the object, but there's also a phase shift. There's a change in the phase. The peaks and valleys here, the wave is might be more closer together or further apart after going through an object. These phase shifts are what we're looking at when we're looking at phase and phase contrast imaging. These phase shifts are microscopic, really small, but when they accumulate, they cause something called refraction. And refraction is the fact of light, in this case, X-rays, changing direction. Okay, so you have light, it reaches an object, and then it changes direction. This is the reason why we get something like this, for example, where you have the pencil in water, and because the light, when it reaches the water, it changes direction, the pencil looks broken, like this. Again, how does refraction work then? Well, we have the object, again, my mouth or my brain or whatever. You have the X-rays coming in, and then they are refracting, they change direction when they hit the object. This is just an example, by the way, of the type of refraction that you can get. The direction can change in many different ways. And this drives phase or refraction contrast, where we get images based on these phase changes that happen in the sample. And actually, this works much better for something like the breast tissue example that I was mentioning before, for soft tissue, than something like attenuation, because the details that we can get are much better. There's a third thing that happens when X-rays hit matter that I wanted to talk to you about. So I've talked to you about attenuation, I've talked to you about phase or refraction, and I want to talk to you about scattering. Okay, what is scattering? Well, again, we have the sample, we have the object, the X-rays reach the object, they hit it, and then if we look closely, what happens when the X-rays hit the object is they start hitting all the atoms and molecules within the object. They start changing direction really quickly, really small at a microscopic level like this. And this is called scattering. And this causes also known as dark field contrast. These kind of interactions actually help us learn a lot about the microscopic subpixel, really small structures of the sample because of these really small interactions that we can get. Now, multi-contrast X-ray imaging, which is what we're here to talk about, is essentially trying to put together all of these different interactions that happen when X-rays hit matter or go through matter in order to learn a lot about that object. Basically, the idea is, okay, we've always used attenuation and that gives us some information, but if we can get even more information from the X-rays, we'll get even better images. Okay, we're focused again. This is a perfect example of this. So we have a mouse imaged with attenuation, with phase refraction, or with dark field. You can see that each of them brings something to the table. So we see here the skeleton perfectly. Here we see, for example, the respiratory system very well, which we couldn't see in attenuation. And here we see the lungs very well and all the hair very well. So each of these contrast imaging techniques brings something to the table, and combining them can help us learn a lot more and see details that would otherwise be invisible. Another example would be this. This is a rabbit brain, and you can see an attenuation image versus a phase or refraction image. Here you can see a lot more details that are not visible at all in the attenuation image. So again, bringing together these different methods can help us learn a lot about a sample. Now, briefly, I just want to talk to you about other imaging techniques. Oh, I disappeared again. Other imaging techniques beyond X-rays, particularly MRI. So often people use MRI to image something in the body, and particularly because it doesn't use ionizing radiation, and often, especially with X-ray attenuation, like these images here, it gives better contrast. It gives better image of what's happening inside. In this case, for example, inside the brain. However, MRI has many severe downsides. It takes a long time. It is very expensive. It is not as readily available and widely available as X-rays are. And it's also quite a claustrophobic process. For someone to do an MRI, it takes a long time. You have to be still. It's actually not very pleasant at all. And if you have metal in you, that could be metal ink or that could be pacemakers, you can't have an MRI. So there are important clinical gaps that we can actually fill using multi-contrast X-ray imaging. For example, with phase contrast, we can actually get much better soft tissue contrast, images of soft tissue, such as the breast tumors that I was talking about. And so we can bridge these clinical gaps where MRI or X-rays with attenuation can't really reach. Now, before handing over to Carlos, I just want to leave you with this. So from all I have said, the only thing or the main thing that I want you to remember is that with X-ray imaging, there is always more than meets the eye. And what I mean by that is that we've always thought of X-ray imaging as this relatively simple thing, right? The attenuation that we've used for several years, almost more than 100 years. But in reality, there are so many things that are happening inside an object, inside a sample when the X-ray goes through, that if we can actually take a close look at all of these things, we can learn a lot about the sample. That's me, so I'll just hand you over to Carlos now.
Thank you, Oriol, for that great introduction to the topic today. As he said, now we're going to become a bit more technical. And we're going to speak about how we develop a technique. Our research group has developed a technique here at UCL that allows you to have access to these three contrast channels. The technique is called edge illumination, and its basic working principle is to collimate the original X-ray beam into very small beamlets of the order of microns. These beamlets are much more sensitive to refraction, which allows us to turn this refraction into a change in intensity. So for instance, if we have a look at this diagram, let's say we align the beamlet 50% hitting our pixel, 50% not hitting our pixel. And then when we introduce a sample that is going to refract the X-rays because of the principles that Oriol just explained, then this refraction is going to turn into more or, well, into less or more counts into our detector pixel. This is very important because we don't have phase sensitive detectors. We only have intensity sensitive detectors. And in this way, we're creating contrast from the refraction principle. This is a technique that has been developed for several years, up to 20 years, by Professor Alessandro Olivo, who came to UCL in the late 2000s. You can extend this principle to translate it to lab and clinical systems by including these absorption masks that certain parts of the mask absorb the X-rays and the others let them pass. For instance, I'm showing here in the bottom one of the images that you can obtain by putting a wire inside the sample. So you have a strong contrast at the edges and negative peak followed by a positive peak. And this is coming from the refraction signal at the edges of our sample. Now, this, as I said, this has been a long process, and at the moment we acquire these contrast channels through something called the illumination curve. So what is the illumination curve? We scan the sample mask over our detector, and as you can see, we have a peak at which we reach maximum intensity. And then as we're scanning it, it drops. This illumination curve is characteristic of each system and gives you properties of the sensitivity of your X-ray system. As you can see, this illumination curve has the shape of a Gaussian. And as some of you might know, a Gaussian can be described by 3 parameters. So these 3 parameters, amplitude, mean, and scattering, give us each one of them information about the attenuation, the refraction, and the dark field. And this happens when you compare the illumination curve for each one of these pixels with sample and without a sample. And for example, this is one of the images we have obtained in our lab. And as Oriol was saying with a different example, attenuation gives you some information about the sample. In general, here you can see attenuation happening in different parts of it. Refraction gives you information about the ages or the change in medium. And dark field, if you see here in the petals, it's giving you information about the microstructure. So actually it's giving you access to those features that are smaller than your system's resolution. And this is shown here in the microstructure of the petal or in the hair in the mouse that Oriol was showing before. Let's look at some of the applications of AI, of EI, and how it's being used for a wide range of industries. So one immediate application is breast tissue imaging because it's low density. For breast cancer, the usual treatment is breast conservation surgery followed by therapy. X-ray phase contrast tomography with edge illumination can provide images in minutes to assess whether the tumor was fully removed or not during one of these surgeries. So here in the left, I'm showing an attenuation image, which shows very poor contrast. And here in the middle, the phase contrast signal that gives you access to these margins and gives you information about the tumor after it's been removed. And it's of a quality that is similar to histological images, which are taken with a microscopy after slicing the tissue, and which are obtained after several days. But our team has managed to obtain phase contrast high quality images within minutes, which can give feedback and assessment to the clinician while they're operating about whether the tumor has been fully removed or not. This extends not only to biomedical or clinical applications, it can also be used to image materials. So for instance, here I'm showing carbon fiber reinforced composite materials, which are highly attractive due to their high strength and low weight, particularly for the aerospace industry. And carbon fibers are brittle and prone to fracture into layers when subjected to stress. X-rays are useful, but the issue is that carbon is low density. So you usually need very high resolution systems to assess the quality and the health of these type of materials. And what we've seen is that with refraction and scattering, at the same resolution or attenuation, we have access to those very small cracks that were invisible unless you use very high resolution systems. And the last application I want to show you is for tissue engineering. So tissue engineering aims for the surgical treatment of tissue loss caused by trauma, cancer, or congenital malformation. And it grows cells from scaffolds or support structures, which could be synthetic or biological. It has been shown simple structures. It has been shown to work for simple structures like skin or bladders, but not for more complex constructs such as the esophagus. And this is because it requires a higher level of structural and functional characterization prior to clinical transition. And here is where X-ray phase contrast tomography can provide volumetric reconstruction with a high level of detail, similar again to histology, without destroying the sample. And here in the image, you can see the layers being retrieved or distinguished for the native, the scaffold, and the recellularized esophagus, which can help you understand this whole tissue engineering process for complex samples like the esophagus. So as any other research strand, there's always challenges and opportunities. Well, challenges to translate it towards clinical practice, and edge illumination has some of them, particularly because, as you saw, you collimate the beam and you need to translate this mask to acquire what we said was the illumination curve, but you also have hidden parts of your sample. And this means you need to translate the sample to fully illuminate it and have information about all the parts. And if you want to acquire a CT, you need to add the rotation to reconstruct the tomograms and the volumetric reconstructions. And this implies, well, you're not using all the flux because you're absorbing a lot of it with your absorption mask. And also it's slow because you need to use motors to scan all these components of your system. So, well, how can we improve these to develop clinical and other applications? Here is where we come in as PhD students and researchers, and many people in our group making huge efforts to translate this technology towards the lab and the hospitals. And for instance, one thing I'm working on is on beam tracking. So beam tracking, instead of using only one pixel and then scanning that mask over that one pixel of the detector, uses multiple detectors, multiple pixel detectors to sample this thing called the illumination curve. Basically, it gets rid of the sample mask displacement. These can get the 3 contrast channels in a single shot, and for instance, open the door to dynamic studies. Dynamic studies is studying a sample over time, and we've done this down to with a time resolution of 22 milliseconds. And by looking at how a laser is melting a powder. This is very interesting for additive manufacturing applications. And we've seen, for instance, that the droplets show first in the phase and the dark field signals because of the principle we've just shown, compared to transmission. And this is one thing that is possible due to faster acquisition provided by beam tracking.
And what I'm working on is something called cycloidal computed tomography, or cycloidal CT. CT is that thing I was showing you at the beginning of the big machine where you go in, you have the X-rays whirring around you, and then you get a nice image of your brain or your lungs. That is what CT is. With edge illumination, because of everything that Catalyst was saying, the need to move the sample in several directions, in several ways, often CT can take a long time. So what we've been doing with cycloidal computed tomography is smart undersampling. And by that, I mean, how few data points can we use moved around in a clever way so that we are much faster, much more efficient than edge illumination, but we get basically as close to the same image quality as we can. This is, for example, some of my results. So this is a traditional EI scan, which took quite a long time. This is a cycloidal scan, and this is what we call a just rotation scan. And just let me explain to you what this is. So these two use the exact same amount of data, which is very little data compared to this. These use 1/8 of the data that this uses, and they take very little time, or a very comparable amount of time. But as you can see, this is much, much worse than this. You can't see most of the details. Whereas with cycloidal CT, using the same amount of time, being very efficient, using less dose, you can see much more details, and it's very, very close to the standard of the traditional edge illumination CT. And I'm working on this with my colleagues, Charlotte, Martina, Yasha, and Amy. Charlotte came up with this method, and we are hopefully taking it even further. So this is our time. Obviously, we're part of the Advanced X-ray Imaging Group. This has been a huge effort that's been going on for many years, and many people have been involved. So we thank every one of them. And if you have any questions, please let us know. Can you tell more about AI applications, image segmentation when working with X-ray imaging? So, I mean, there are a lot of AI applications. There's a lot of machine learning. There are a lot of machine learning possibilities. Myself, I have worked on improving the cycloidal images that I showed in the last slide. Let's just quickly go to that. Can I go to that quickly? Nope. No. Okay, I myself have worked on improving these cycloidal images with machine learning. In terms of image segmentation, I mean, yes, that is something that is important for X-ray imaging, and particularly that is being researched as well. I know my colleague Savas, for also the esophagus paper that Catalyst was talking about, did a lot of image segmentation. It's a huge field. Yeah, I don't know.
Maybe I would change the order of the question, in the sense that, okay, what can AI do for us? Yeah, so what we can do for AI is provide data, basically. Yeah, which is what all the artificial intelligence applications need. And then from there, I would say it's more a thing of what we can get from machine learning and artificial intelligence to help us get this technology farther towards clinical practice. So one of the things that Otto was saying is that if you want to work on the subsampling and faster acquisitions, then machine learning could enter there to help us get faster acquisitions with basically lower data, and then complete the data sets with machine learning or any AI deep learning. So that's definitely one of the things. And for image segmentation, for instance, it just means that now, instead of having just attenuation CTs, we also have phase CTs. So as I said, it's just more data that we can provide for AI to develop novel algorithms for our purposes, applications, and towards taking this to clinical practice.
Okay, we hope that helps. So what is the raw difference in time between the fast and slow scans on the last slide? Thank you for that question. So the difference in time is this scan on the left, the let's say normal scan, or the normal EI scan. This one I think took almost 24 hours, whereas these other two can go down to 20 to 30 minutes. That's it. Then let's see what else. So, okay. May I please broadly ask, does AI have a scope in gastroenterology? So I'm sure it does. I'm not an expert in the field at all, but I'm sure it does. In terms of imaging, possibly in terms of surgical advances. Yeah, I'm sure.
Yeah. In general, providing information that has been hidden whatsoever. So yeah, there's big efforts to explore different areas and different organs within the human body. So we showed esophagus, but there's big efforts to do rat heart imaging towards cardiovascular system. So yeah, it's an extensive effort that has extended to many different parts of the human body because of the context it can provide. Yeah.
How long does your current EI acquisition take? So it depends. It can take several hours, even several days, depending on what the parameters are. But this is obviously, or this is in a lab setting, whereas this can be for commercial purposes or for clinical purposes can be significantly sped up.
So one of the things that is taking the time at, for instance, in typical edge illumination acquisition is motor movement. So one of the things that we do is that we move a motor, we take an image, move a motor, we take an image. And this is how it's done at the lab. But when you want a clinical system, then you would do a fly scan, which means your sample is constantly moving while you're taking snapshots of your sample. And this has been managed to speed up out to the order of minutes. So the breast tissue specimens I've shown with all the optimization has given us images within between 20 and 30 minutes. So that's the fastest it's been possible with all of these optimizations.
But again, this might come at the cost of high resolution or high quality, and hence where something like cycloidal CT comes in.
Okay, I'm not entirely sorry, I'm gonna read it again. So you see the application about crack detection in carbon fiber. The next generation jet mostly built in carbon, but I don't have idea about the size of it, which fit the aircraft maintaining. Not entirely.
So I'm not entirely sure what you mean, but I don't know how big were the composites. Do you know?
So at the moment, the field of view is of the order of centimeters. It should be around between 4 max 5 centimeters. This is all prototypes, but of course this is a scanning of aerospace parts. So they're usually scannable. These non-destructive evaluation techniques are used in the process of building these airplane parts before assembling them together. I don't know if this is giving you any information about what we were asking.
If you want to elaborate on your question, put it in the chat, and then Naomi will unmute you at some point. So the next question is, are there modifications to conventional CT scanners for cycloidal CT? So for edge illumination in general, the only modifications really that you need are the masks, are these absorbing masks that Carlos was talking about that help you collimate or basically restructure the X-ray beam into narrow beamlets. And with cycloidal CT, that's also the only necessary step, the only necessary modification in order to use it. There are some considerations about resolution, about, well, how the source is, how the X-rays spread onto the sample, but in general, you mainly just need the masks.
Okay, so is it possible to generate synthetic X-ray imaging and explore techniques you talked about without direct access to hardware? Yes, definitely. Actually, this is what we do before. So the way this research pipeline works for us is new ideas are usually tested through modeling. So we know how X-rays propagate, how they interact with matter. So we propagate X-ray waves. We model X-ray interactions for attenuation, phase, and scattering. And then we model our X-ray detector, and we know how they work. And all this modeling can be used to simulate, as you just said, edge illumination systems, or almost any X-ray system, to be honest. If you're interested in this, feel free to get in touch. We can give you more details.
Yes, we didn't put our emails in, but we can do this. We'll put them in the chat before we leave. I was thinking about the size. They were thinking about the size of the X-ray machine, since the aircraft carbon crack detection may need to size to be handheld. Yeah, so I think yes, there is a limitation of field of view. as always, and this will hopefully only improve as the edge elimination science improves, and field of view might grow. But yeah, there is limitation for now.
Yeah, there's limitation that has turned into opportunities and new ideas to like scan big samples over a determined field of view, so that you can actually retrieve information from like different parts of a very big.
Charlotte is helping Ling.
Okay, yeah. So yeah, there are strategies to like image very big samples within smaller field of views. This is also limited by current detector technologies, but there are already systems that have been developed for aerospace applications. Let's say that now the goal is to incorporate EI and these masks for these already existing technologies and solve their limitations.
Do you think that the EI technique could be implemented in medical CT scanners, or would they need to be specialized machines? Okay, good question. I think, to be quite honest, I'm not sure. I think I'm not sure that in a CT scanner right now at a hospital you could immediately implement it just by bringing the masks. I'm not sure. I'm generally not sure. I think the difficulties are minimal, but I think I'm not sure actually. I'd rather not. I think in medical CT scanners probably because we're talking a lot about micro CT, about really small resolution. So when you're talking about medical CT scanners, actually you're really talking about much bigger field of views. So for a CT scanner that you'd use to image, for example, a body, I don't think it would be immediately translatable right now, just in terms of having a mask that is big enough to cover the whole thing.
Yeah.
I think, I'm not too sure, don't quote me on this too much, but there's a new message. Yeah.
Yeah, there are efforts already with other techniques that have managed to put these kind of masks and gratings and actually image lungs. There's a very big study that came out not very long ago on lung imaging and COVID actually as well, specifically using the scattering signal, and this has been incorporated into CT scanners already existing. With edge illumination, we're aiming to get there. At the moment, the efforts have been to develop new systems from scratch, let's say a dedicated system for edge illumination rather than incorporated into existing CT scanners. But yeah, it still hasn't got there.
Okay, so I think that those are all the questions. If you have anything else, do type it or ask. So I'm just going to type my email as well. Okay. Can't type it. So yeah, so feel free to contact us if you need anything, have any questions, and we'll do our best to help.
There you go.
There you go. Thank you very much. Yeah.
Fantastic. Thank you so much, Carlos and Oriol. That was a really fascinating lecture, and great to see so many questions coming in and potential future collaborations as well. So brilliant. Thank you so much, everybody, for attending. That was a really great session, and I popped a link to the next Spring into STEM lecture in the chat. It's a little while ago, so I'll pop it in there again. But thank you so much for joining us, and again, thanks Carlos and Oriol for such a enlightening presentation as well.
Thank you very much.
Thank you, Naomi. Thank you, everyone, for joining.
Thank you, everyone.